Okay, so now let's look at some modeling. In the beginning of this unit, we talked about our different exponential formulas, starting with our basic y equals a times b to the x, where a is our initial value and b is our multiplier. Anything that grows or decays by a percent, we then have to use 1 plus or minus r to get that base. And then if it is compounded a certain number of times per a time period, we got this third formula. Then we discussed the continuous growth and decay formula, and that's where that base of e comes from. And so that's the formula a equals pe to the rt. It's the same thing as saying y equals a e to the rt, where if it grows, the rate is positive. If it decays, the rate is negative. We're now going to use these same formulas like we did at the beginning of the unit, but instead of using graphical methods and tabular methods to solve the problem, we're going to use the algebraic methods we have learned over the last few lessons. So Mr. and Mrs. Smith invest $10,000 in a CD that is compounded continuously for their daughter to go to college. In 15 years, the CD will be worth $25,000. What is the interest rate of the CD? And if you don't know what a CD is, it's a certificate of deposit. It's a special type of savings account. So because this uses the term compounded continuously, that's the key words that we know we're using this PERT formula. So I'm going to go ahead and write down our formula first. We have A equals P e to the RT, where the principal in this case is $10,000, and it's eventually going to be worth $25,000. We do not know the rate, but we know that the time that has elapsed has been 15 years. I left my E out right there. So the first step, just like any exponential equation, is to isolate the base. So to isolate the base in this case, we would divide each side by 10,000. So that would leave us with 2.5 is equal to e to the r times 15, which we can go ahead and write as 15r. Now that we've got that base of e by itself, we can take the natural log of each side. So the natural log of 2.5 is equal to the natural log of e to the 15r. The natural log of e, they undo each other, so that's just the natural log of 2.5 is equal to 15r. And then last but not least, we would divide each side by 15 to get that rate by itself. So you would type the natural log of 2.5 divided by 15 in your calculator, and that gives us that r is approximately 0.0611. And most of the time they're going to represent this as a percent rate. So that means that the rate was approximately 6.11% per year compounded continuously. Okay, so looking at the next problem, the population of the United States is continually growing. Again, look for those key words, continually growing. In 1992, the population of the United States was 246 million, and the exponential growth rate was 0.9% per year. How many years after 1992 will it take the U.S. population to reach 300 million if the exponential growth rate remains at 0.9%? So again, this is one of our PERT problems. Now, since the initial amount in 1992 and the final amount of 300 million are both in millions, we do not need to add all those zeros in here because it would just divide through when we set it up. So we can just put for our principal 246, knowing that that's in millions, and our final 300 million. And then we have E, and in this case, our rate is 0.9%, but guys, that is still given to you as a percent, so you have to change it to a decimal. I know it's a decimal, but you still have to understand that percent out of 100 and move that decimal place 2 places to the left. So that is going to give us 0.009. And so we'll set this up raised to the 0.009, and we're solving for t. All right, y'all solve it. When you're finished solving it, start the video back. Pause now. So the steps for solving this problem is just like the last problem. We isolate that base. Once we get the e by itself, we take the natural log of each side and then divide through by 0.009. You'll notice that when I typed 300 divided by 246 in my calculator, I got a really ugly decimal, and then I changed it back to a fraction because the last thing I want to do is start rounding in the middle of our problem. If we do that, we can get our answer extremely off. In the end, we get just a little bit over 22 years. And even though this said about how many years, in case you had a problem where it said in what year, since this started in the year 1992, if we add 22 years to that, it would happen sometime in the year 2014. All right, so looking at the next example, for a certain radioactive element, K is negative 0.377 when T is measured in days. How long will it take 500 grams of the element to reduce to 200 grams? Okay, so going back to our formula, our PERT formula, if I rewrite it like this, y equals a e to the RT, sometimes instead of r, they'll put k in this formula. It's the same thing. A lot of times, though, when they give it to you as k, k is already in that decimal form. Notice how k does not have a percent on it. So this is the formula we're using to set this up. So our initial amount is 500 grams, and in this case, it actually reduces to 200 grams, which is why that k value right here, which is the same thing as your r value, is negative. That's what makes it decay. And then we will put t in here. So this is going to work out just like the last one. Pause the video, solve it. When you're finished, start the video back. Pause now. Okay, so if we work this out correctly, we should get that it would take about 2.4 days. And that makes sense because if you actually changed that constant rate back to a percent, it was decaying by around 37.7% each day. So that's a big amount to lose daily. So the next problem, suppose that Keith has $1,200 to invest. His investment will earn an interest rate at 6.5% compounded continuously. To the nearest cent, what will be the value of Keith's investment after 6 years? To the nearest tenth, how long will it take for Keith's investment to grow to $2,500? And then part C, to the nearest tenth, what interest rate would be needed to triple Keith's investment in 15 years? So for part C, you will not use the 6.5% interest rate because it's changing the question. So I want you to go through and do these. Make sure for part B and C you're using the algebraic methods. If you want to back yourself up by using a graphical method like we did at the beginning of the unit, that's fine. But the purpose of this is to now learn those algebraic steps for solving. Okay, pause the video now. The first part is just straight up just being able to recognize which formula to use, substitute everything in, and make that calculation. The next one wants to know to the nearest tenth, how long will it take for Keith's investment to grow to $2,500? Okay, so we set everything up and we're solving for the time in this case. We are working this out algebraically. So we divide each side by 1,200. Then once we isolate that e, we take the natural log of each side, and we ultimately, after solving for t, get about 11.3 years. Now, folks, on an assessment, if I give you a problem like this, whether you have a calculator or not, if I say to solve it algebraically and you do not show me this algebraic work, you would not get full credit. So it's really important that you know how to do these problems algebraically and graphically. The graphing is a great way to back yourself up. All right, the third one. So very similar to the last one, the only difference is we're solving for the rate this time. We want to triple the investment, so that would be $3,600. I want you to notice right here in this step, when you divide through by 1,200, you pretty much get this ratio right here, 3 equals e to the 15r. Folks, I've seen problems before where they never told you the initial value. They could have just asked part C and said, to the nearest tenth, what would be the interest rate needed to triple an investment in 15 years if it's compounding continuously? It doesn't matter what amount you start with. The amount of time or the rate that it would take to triple that any investment is going to be the same. And that's why you get that 3-to-1 ratio right here. And I just want to point that out because I've seen those problems and students are like, there's something wrong, there's a missing piece. It didn't tell us how much to start with. It doesn't matter. You could make it up because every time you divide through, it's going to give you that 3-to-1 ratio. Okay, so for this last one, we're going to work on this one graphically. It says Samantha invested $10,000 in each of 2 different financial plans in 2013. The predicted value of each plan is modeled below. For Plan M, a rate of 7.5% compounded continuously. So again, keywords right here. Compounded continuously, so we need to set that up. So the formula for that would be y is equal to 10,000 e to the 0.075 t. And since we're going to use our calculators, you might even want to put x, knowing x is t. Then plan M, the value is determined by the following function, and it gives us this cubic function, where x is the number of years after 2013. During which years will plan N have a greater predictive value than plan M? That should say have, not has. The first step is going to be to type both of these functions into our calculator. And guys, it's really important that you actually do this and not watch me do this, because if we have a little assessment and you can't type this in your calculator, I'm not going to help you. You have got to learn how to use your calculators, how to use those tables and those windows to manipulate what you need to see. All right, the next step is you always want to go to your table. All right, so go into the table, second graph, which is our table. We can see that at year 0, they're the same. And that makes sense because they both had that same initial value of 10,000. But what you notice is the first function is out growing a little faster than the second function. But as we scroll down and look at it, after a little bit, somewhere here in year 30-ish, the second function actually gets to be a little bit more than the first function, right here around 2930. And then if we keep going, you can see that that first function actually comes back and surpasses that second function. Well, what I wanted you to look at here is the numbers that we're dealing with. So we said that happened around 29 and then to 61. So those are the x values we need to see. And look at these y values. When we get to 62, they start getting in the millions. So that's what helps us set up our window. So when I come here to my window, and I'm going to real quickly fix this by pressing Zoom 6 and just putting that back in a standard window, which isn't going to show us what we need to see. But that just fixes my window in case it's messed up. Well, I want my X max to be past 60-ish. So maybe I make my X max around, I don't know, 70 or 80. There's not a magic number, but you definitely want a little buffer on there. And if I do that, I'm going to make the X scale 10. Well, that Y max, I mean, we were getting into the millions there. So I might make mine 100 or 1,100,000. And if I do that, I'm definitely going to make my Y scale a lot bigger, or it's going to be extremely thick. So I'm going to make it 100,000. And your Y min, you may want to make it have more room. If not, your Y axis is so low on the bottom of the screen. If that doesn't bother you, that's fine. But I might make mine negative 100,000, just a little buffer there so I can kind of see what's going on. And then graph those two functions. And what happens is that red one is a piece of that cubic function. But that blue one, even though it dips below it, you can see when you get over here to this second intersection that it's finally going to surpass it. Because guys, in the long run, an exponential function grows faster than any other function. All right, so what we want to do is find those intersections. So to do that, we're going to press second trace. We're going to go to number 5, intersect. Your calculator is not a brain. It does not know which one you want, so you want to scroll over by each one. So I'm going to press enter, enter, enter. I'm going to write that intersection down. Do it again to get the next intersection. So second trace, we're going to go to number 5, intersect. We're going to scroll over by that intersection so our calculator knows which one we want. When we get by it, press enter 3 times, and we're going to write that intersection down. To get our final answer, we would add those years to 2013. So if it's been 28.3 years, it would be somewhere 28 years after 2013. So you're going to add that, put us somewhere in the year 2041. And then we're going to say 2013 plus 60 and a half years. And that's going to put us somewhere in the year 2073. So we would say between 2041 and 2073.